In this lecture, I will explain diode equivalent circuits, but first we will try to understand what is an equivalent circuit. An equivalent circuit is a combination of elements like resistor, capacitor, inductor, etc. properly chosen to best represent the actual characteristics of device in a particular operating region. So in equivalent circuit, we choose elements like resistor, capacitor, inductor to best represent the actual characteristics of the device like diode, transistor, etc. in a particular operating region. Now there is one question: why we need equivalent circuit? Why we need equivalent circuit? We cannot use traditional circuit analysis techniques like Thevenin's theorem, Norton theorem, superposition theorem with actual device. If you have diode or transistor in your circuit and you want to use the circuit analysis techniques like Thevenin theorem, Norton theorem, etc. to find out parameters like voltage, current or resistance, then you cannot use them with the actual device. And once the equivalent circuit is defined, we can replace the device symbol with equivalent circuit and solve it using traditional circuit analysis method. So it's very simple. If you want to find out parameters like current, voltage or resistance, or simply if you want to solve this circuit in which there are devices like diode, transistors, etc., then first you have to replace the device by its equivalent circuit so that you can use the circuit analysis techniques. So this is the reason why equivalent circuits are so important, and in this lecture we will try to find out equivalent circuits for diode. We will study three types of equivalent circuits. The first one is piecewise linear equivalent circuit. Linear equivalent circuit. The second one is constant voltage drop or simplified equivalent circuit. And the third one and the last one is the ideal equivalent circuit. The third one is the ideal equivalent circuit. In the last lecture we have already completed the ideal equivalent circuit, and we will start with piecewise linear equivalent circuit. There is only one assumption in piecewise linear model. We will assume the curve to be linear even with small non-linearity. I will write this down. We will assume the curve to be linear even with small non-linearity. So this is the only assumption in piecewise linear model. And first I will plot the curve, and then we will draw the equivalent circuit. The y-axis is for ID and the x-axis is for VD, the voltage across the diode. And if we consider the forward bias condition, then we have something like this. This voltage is VB, the barrier potential, and first we will try to find out the diode resistance RD. The diode resistance is RD, and it is equal to 1 by slope, the slope of this curve. And you can easily find out why it is equal to 1 by slope. We already know slope is equal to tan theta. From mathematics we know slope is equal to tan theta, and tan theta is equal to perpendicular by base. So we have slope equal to ID by VD. This is what we have. And from Ohm's law we know that VD is equal to ID RD. So if we rearrange this, we will find 1 by slope is equal to VD by ID. And from here you can see, if we divide both the sides by ID, this will give us Vd by Id equals to Rd. So this we can replace by Rd, and the diode resistance is equal to 1 by slope. So by calculating the slope, we can easily find out the diode resistance. And now we will draw the equivalent circuit. In this model, we have the barrier potential Vb and the diode resistance Rd. In the equivalent circuit, first I will make the ideal diode. In ideal diode, both barrier potential and diode resistance are equal to 0. And we are using the ideal diode, the symbol for ideal diode, to represent the direction of current. I will write this down. We use this to represent the direction of current. And then we have the barrier potential Vb. From the plot you can see we have the barrier potential Vb, and the barrier potential opposes the flow of current. So the polarity will be like this. This will oppose the flow of diode current, and there is diode resistance Rd. This is the diode resistance Rd. This is barrier potential Vb, and this is the equivalent circuit for diode in case of piecewise linear model. And we connect P side to the positive terminal, and this side we will connect to the negative terminal, and this is the voltage across the diode Vd, and current through the diode is Id. So this is the model or the equivalent circuit for the diode in case of piecewise linear model. In this we have the barrier potential Vb, and we also have the diode resistance Rd, which you can easily calculate by using this slope. So let's try to find out the diode resistance. I will take one example in which at 0.8 volts the diode current is 10 milliampere, and we have to find out the diode resistance Rd. It is very simple. Rd is equal to 0.8 minus 0.7. The barrier potential in case of silicon is 0.7 volts, and in case of germanium it is 0.3 volts. So we have 0.8 minus 0.7 divided by current is 10 milliampere at 0.8 volts, and it is 0 milliamperes at 0.7 volts. 10 raised to power minus 3 for milliamperes, and when you solve this you will find the diode resistance is equal to 10 ohm. So this is how you can find out the diode resistance in case of piecewise linear model, and this is all for this first model. Now we will move to constant voltage drop model or simplified model. In electrical circuits, resistance of diode is very small as compared to the resistance of other elements, so it can be neglected. There are two assumptions in the second model. In first assumption, we have to consider the linear curve instead of a small non-linearity, and in the second assumption we will consider the diode resistance Rd equal to 0, and when Rd is equal to 0 it means 1 by slope is equal to 0, or we can say that slope is equal to infinity and slope is equal to tan theta. So tan theta is equal to infinity, theta is equal to tan inverse infinity, or theta is simply 90 degree. So in case of constant voltage drop model, we have theta equal to 90 degree. This is theta, and in this case it is equal to 90 degree. So it is very easy to plot the curve Id Vd. We still have the barrier potential Vb, but the diode resistance is equal to 0. So we have plot like this. This is theta equal to 90 degree, and this shows the diode resistance Rd is equal to 0. This is Vb, and it is equal to 0.7 for silicon and 0.3 for germanium. So this is how the characteristics looks for constant voltage drop model. Now we will make the equivalent circuit, and it is very simple. If we compare the equivalent circuit with the first model, we will find there is no diode resistance. So everything will remain same, and we only have to remove the diode resistance. So I will draw it quickly. First we will make ideal diode to represent the direction of current. This is the ideal diode. Then we have the barrier potential VB, and diode resistance is equal to 0. So there are only two things. First one is the ideal diode and second one is the barrier potential. We will connect P side to the positive terminal and this side to the negative terminal, and voltage across the diode is equal to VD. Current through the diode is ID. So this is all for the constant voltage drop model. Now we will move to the third model, that is the ideal model. And in case of ideal model, both diode resistance RD and barrier potential are equal to 0. This is something we have already covered in the last lecture, that the diode resistance is equal to 0 and barrier potential is also equal to 0 in case of ideal equivalent circuit. And it is very easy to plot it. In forward bias region, as barrier potential is equal to 0, we have plot like this. This is ID and this is VD. Barrier potential VB is equal to 0, and as the slope is equal to infinity, the resistance of the diode is also equal to 0. And if we make the equivalent circuit, then it will look something like this. There is only ideal diode, barrier potential is equal to 0 and the diode resistance is also equal to 0. So there is only ideal diode, current through the diode is ID. And if we compare the three models, we will find in the first model, in the piecewise linear model, we have barrier potential VB, we have diode resistance RD, but in second model, the constant voltage drop model, the diode resistance RD is equal to 0, so we only have the barrier potential. And in the last model, the ideal model, both barrier potential and diode resistance are equal to 0. So this is all for the three models, and if we compare them, then we will find the constant voltage drop model is mostly used. This model is mostly used. When you solve numerical problem, you have to use this model. And in numerical problem, if the diode is forward biased like this, if the diode is forward biased, this is 5 volts, this is 0 volts, then you have to replace the diode with its barrier potential. 5 volts and 0 volts. And if it is given that the diode is silicon diode, then the barrier potential is equal to 0.7 volts. And now you can easily solve the circuit. And if the diode is reverse biased like this, if the diode is reversed bias, this is 0 volts and this is 5 volts, P side is connected to the low potential and N side is connected to the high potential. So this is the reverse bias condition, and in case of reverse bias condition, there will be no current through the diode, so it will act as open circuit like this. These 2 points are very important, and by using them we can easily solve the numerical problems. In forward bias condition, you have to replace the diode by its barrier potential, and in reverse bias condition it will act as open circuit. So this is all for this lecture. See you in the next one.